Welcome everyone out there all over the world. This is the fifth episode of the Masterclass Mondays. We are happy that you are here, that you want to become an embedded wizard expert yourself. My name is Kristen. I'm responsible at Terra Systems for marketing and communications. And today you will learn about the platform package and the build environment. As usually, we will be recording this session and will be put it up later for you to recover it. And then I want to hand over already to Manuel Milic, our product manager, who will again guide you through today's topics. Let's getting it started. Manuel?
Yeah, Christine, thank you very much for the pleasant introduction. Good morning, good afternoon, good evening to all our attendees worldwide. It's really a pleasure to have you here in this fifth episode of the Masterclass Mondays. And as Christine already mentioned, our topic for today is the so-called platform package and the build environment. So, what is this platform package all about? This is something that I'd like to give you in the very first overview in order to explain how we structured our system. And then we talk about the graphics engine, we talk about our runtime environment inside the platform package, and finally something that you probably already might have seen is this so-called build environment. So what's this all about? And I'll give you an more deep dive how this is overall structured. So let's get started. And usually I would now go ahead with the studio, but in that case I'm still sticking here in my slides. So we will not focus much inside the studio. Anyway, I'd like to give you a brief overview how Embedded Wizard's core architecture is made of. In fact, we have the studio, so that's the IDE where we have spent now quite some hours meanwhile to develop the GUI, to prototype, to let Embedded Wizard also generate the sources at the end. And how this generation process is structured and is defined is mainly maintained by the so-called platform package and dictated by the platform package. So the platform package itself tells the studio how the sources are generated, and therefore the so-called code generator comes into place. However, when the sources are generated, the default way is also to convert the dedicated resources. So that means the bitmap resources and the font resources. And how these are now also converted, generated into ANSI code, for example, this is all defined by the platform package. And that's the reason why the platform package itself needs to be installed also on the PC. So the studio, when you select the dedicated profile, and then you select also for which kind of perhaps let's do it this way. Just remove that and start Embedded Wizard Studio. And just create a new project, which is our master class episode 05. So create a new project. So new project generated. Selecting the profile gives you an indication which platform package is used. And the number of available platform package, this is defined by which platform package you have installed on your PC. And as you see on that PC, in that environment, I've installed quite a couple of. So the Android platform package, a Raspberry Pi platform package for various STM32 microcontrollers, microprocessor, an OpenGL platform package which comes into place when we are going to, for example, NXP MPUs. We have a generic platform package without any hardware acceleration, so that means a pure software-only environment, usually used also for MPUs that do not support a dedicated hardware acceleration. We have the so-called JavaScript WebGL platform package and all our Win32 platform package, which are deployed per default. So you do not need to install the WebGL or the Win32 platform package. They come with every pre-installation of Embedded Wizard. Next to the platform itself and the manufacturer, so for whom is it all about, for Raspberry Pi, etc., it's also indicating which color format to be used. And by selecting the proper platform package, Embedded Wizard itself then also takes care to display inside the prototype or inside the simulator which how this dedicated UI should look like depending on the selected platform package. So as of now, it's selected RGBA 888, so 8 bits per color format for red, green, blue, and alpha. So 32 bits in total, or RGB 32. When selecting, for example, Luma 44, which is luminance alpha, 4-bit each inside 1 pixel, so that means it's a grayscale color format, then this would be a monochrome UI at the end. So let's see how this works. Going to the application, a very simple one, using a rectangle, make that rectangle bigger to have more visible space at the end, and now selecting different colors. So for example, a very blue one on the bottom left, and some green on the top left, and just to make some, and top right, some red color, for example. So a very colorful rectangle at the end. And due to my fact that I have selected the profile, everything is now displayed in a full color space. Just remember, this is currently selected RGBA 888, and when I now go ahead or just make a new profile, so copy the new profile and paste it and say, okay, this is, and rename it, the previous one, it's profile underscore RGBA 8888, whereas that one goes to profile RGB 565. Selecting now Win32 RGB 565, and just make a copy and make a new paste of it and say, okay, not RGB 566, that's wrong. Let's just say RGB, sorry, going back, let's say Luma 44, so luminance alpha 4-bit each color format, and of course selecting now the proper platform package. And when I now go back to the application with a very colorful rectangle, and depending on which profile I am now selecting, so RGB 565, then you already, I hope that you see that at your side in this webinar, there are some not so nice effects, some tearing effects, and these kind of stair effects inside that rectangle due to the fact that you do not have the full color space available, and so it is not so nice looking, and you probably see that very well when now selecting Luma 44, the grayscale, of course, to show a proper and full color rectangle now with only monochrome and grayscale. And you see that this is now not done in a proper way, but you see now this different kind of grayscale formats and shades inside that rectangle, and how this would now made visible and also made visible on the final target when selecting that kind of platform package. So the platform package itself defines now, in fact, for which target should now Embedded Wizard generate the sources in which color format. And the color format especially is then crucial when it comes to generate or convert the resources like the bitmap formats. And this is something that you need to take care about when, for example, adding new bitmap resource, where you can define also dedicated bitmap format or color format for one bitmap. If you do not have a color format set for your platform package with a full color space, so not RGBA 888, for example, and then you might wonder, okay, why is my fully sophisticated bitmap look so not creepy, but it doesn't look as expected, and this could be sometimes the reason why you have selected a different color format, for example. Okay, so inside the studio, you see which currently installed platform package are available by selecting the profile and by selecting the platform package member. And when selecting now different platform package, Embedded Wizard knows how to make them visible during the editor, or when you are inside the composer here, like that one, and how to convert now the resources when it comes now to the code generation process at the end. So just going back now to the slides, so we have here the platform package and the code generator and resource converter. However, the platform package is divided in two parts. What we have just seen is the platform package which is installed on the PC. However, the platform package itself is also tailored for a dedicated target. Hence, it is structured in such a way that depending on the platform package, you have different kind of runtime environments and graphics engine. So what is this runtime environment? What is this graphics engine? Well, graphics engine, I think that's, as the name already implies, very easy to answer. It's the engine to render the graphics, the graphical user interface on the display. So that means there are the basic functionalities for copying an image, for blending an image, to draw a rectangle, to draw a line, also the functionalities to draw the vector graphics, for example, that we already have seen in our last Masterclass Monday session. And this is all implemented inside the graphics engine. However, the graphics engine itself is then also seen as some kind of abstraction layer to the underlying system. So that means, for example, if you have a hardware that supports different kind of hardware accelerated environments, like for example on the MPU, OpenGL, OpenGL ES 2.0, or on the MCU, where you have the pixel pipeline for NXP or the DMA2D for ST as of now, then this is something which is then adapted and utilized in a proper way inside the graphics engine. So that means when you then draw a rectangle, for example, then the depending on the configuration and depending on the implementation of that adaptation layer, the graphics engine, then also the hardware acceleration part is then used. And this one makes it now so tailored and special due to the fact that every platform package is then adapted to the proper underlying embedded system. Next to these graphics engine environments, there's also the so-called runtime environment. And runtime environment, as the name implies, is the environment that is used, for example, to create objects. That's the environment to create strings, to deal with the strings, to do the math. So everything around Embedded Wizard, or around the GUI project, in order to make things alive. There are things like the timers are there, etc. And this is also something that can be now tailored and adjusted and adapted to the underlying system. Just think about a Linux system, for example, is somehow structured in a different way than compared to a microcontroller approach, where you have, for example, no operating system at all. So that means a bare metal approach. And this is something which is then taken care inside runtime environment. And as the name implies, it's the environment to let Embedded Wizard an Embedded Wizard GUI run entirely on your system. And this is now something, so both components are then these parts that needs to be set up and used and compiled and linked on the embedded system. For example, another thing that is also built inside the runtime environment is the entire memory management. So you give Embedded Wizard a dedicated workspace, and then the built-in memory manager, the built-in garbage collector, then takes care about allocating the proper RAM, takes care about releasing and freeing the dedicated memory if it's not used anymore, etc. And this is something which is also built inside the so-called runtime environment. So coming now back to the agenda, where I defined on the platform package, graphics engine, runtime environment, I also said that this topic for today is also now the build environment. So what is this build environment? Perhaps you have seen that because you already registered at our website and downloaded the proper build environment for your desired target. So in fact, when looking at the overall architecture, how a GUI is set up, then we have the following components and logical elements found inside the whole architecture. First of all the red elements are elements related to Embedded Wizard. Of course, inside the main application, an entire firmware application or own binary executable when coming to the MPU part, then you usually have some kind of main application which does the proper initialization of the UI, which does the initialization of the platform package, which does the initialization of any target specific stuff. It does also initialize drivers, underlying BSP parts, the SDK from the system, etc. So this is something which is usually maintained and usually implemented by our customers. The GUI This, and therefore I'm just referring now to the generated sources. This Embedded Wizard GUI part, this is now the entire output that comes from the Embedded Wizard Studio. So that means, and this is also a question that we receive from time to time, I'm so sorry I cannot use Embedded Wizard because Embedded Wizard generates my main loop, or Embedded Wizard generates now the initialization of my system, and I have other peripherals, I have other timings, etc. I cannot use Embedded Wizard. No worries. Embedded Wizard only, or the studio only, generates the sources depending on your user interface. So everything around initialization, usage of drivers, usage of your middleware components, etc. This is something which is not generated by Embedded Wizard. So don't get worried. In fact, we only have here the generated sources, and this is something which is only the entire GUI, and that's it. Everything else is static code. It's not generated, it's not modified, it's not adapted, etc. So it's very static code. So we have the main application, which does the initialization of the GUI, platform package, etc. And of course we have on the underside, or on the lowest level, we have the operating system, if any. We have drivers to be installed, to be used, to be set up, parts of the BSP SDK. And as you see, the color itself already implies that this is something which is usually not deployed by us. However, now talking about the so-called build environment, this is something which we deploy to our to our customers as a template, as a ready-to-use environment. Some people also say this is some kind of SDK to get started or to get started, but we call it build environment because it's something not only source code, it's also enhanced with project files, it's enhanced with examples, it's enhanced with a compiler, with a proper toolchain, etc. in some cases. So it's more than just software and project files. However, there's also a main application built inside this build environment, and this is something that we suggest to our customers to use as a starting base. You need to start somehow and somewhere, and this is something that we can, or the customers can use as a starting base, as a reference. Please keep in mind, but this is something, as far as I remember, that I already told in our last session, that this build environment where the main application and the driver initialization, etc., that this is something that you do not need to follow 100%. It's just a template, it's a reference in order to see how everything is set up, to see how everything is structured, how everything is initialized, and this can also be used for your application. So if you have a total different file layout, a total different setup of your toolchain and file structure, etc., no worries, use it. We see ourselves from a whole architectural point of view as just one part of the main application. Of course, this is now focused on the GUI, so this architecture here, but in fact there are different other components, there are other third-party modules usually inside your firmware or binary executable application, different other libraries, your own business logic, your own middleware, etc. And this is something where we say, okay, we are just one part of that. So we are not dominating the entire UI application, we are just one part of it. And so what comes now from Embedded Wizard? As I already said, the generated sources, these are the sources that comes from the studio, so C files and H files when it comes to the under-C code generation. Then we have the platform package, and just remember one slide back, on target, it's here just the runtime environment and graphics engine. That's it. A couple of files that needs to be hooked into your system and added to your makefile, into your project file, compiled, etc. And then inside our build environment, in order to make our as well as our customers' life a little bit more easier, we added the so-called target specific files. And usually you identify those inside this build environment with the so-called _BSP_ depending on the module file. But we will have a look at that later, what these all are all about. But as said, and this is something which is now a little bit not so precise from the color, because sometimes we say, okay, this is now the structure, how Embedded Wizard, or what we think that it's the best way to initialize the system, how to drive the system. And there are of course some parts built inside which are target specific depending on the drivers. For example, if you have a touchscreen driver that does not report the touch coordinates mapped one-to-one to the screen resolution. Just think about, you have a display with 800 by 480 pixels and the touch driver reports the coordinates with 1024 by 1024 pixels. And this is something where you need to do some scaling, some kind of calibration, some kind of transforming from the touch input in order to match now the expected one-to-one format from the screen resolution to the touch screen resolution. And this is something that you usually would do now in this target specific adaptation layer. And then finally you have, of course, any operating system, if any, or any usage of that. You have your drivers, you have your business board support packages from the platform, system dependent SDKs, everything. And this is now just our ideal view how things are structured. However, it could be that, for example, inside the platform package, there's a usage for OpenGL, and this is something which you will not find in the target-specific adaptation layer, because from our point of view, OpenGL is already some kind of adaptation layer to the underlying 3D core, and this is then something that would then be in this layer, but sitting next to the target-specific adaptation layer and used entirely already by the platform package itself, so inside the graphics engine, without routing that in an extra way to the target-specific adaptation layer in order to reduce the overall footprint, of course. So when it comes to a real application, so what should now be adapted? So usually the generated sources, no worries, so these please do not adapt, because they are generated out of the Embedded Wizard Studio. You have the platform package and especially graphics engine runtime environment, and also please do not make any modifications there, except there are two files, but this is something I'll show you later on how to adapt them and what they're all about. And then, of course, which is the main part in order to adapt, is the so-called target-specific adaptation layer, and of course your main loop. How Embedded Wizard is initialized and driven depending on your requirements, depending on your system. So I've now talked about the overview. I've talked a lot about different components. I would say now it's the best place to really jump now into a build environment in order to see how this is now structured. And this is just an example. So the used build environment as of now is something that we deploy for our adaptations for the NXP RT1050 board in that way, but please do not judge on me. It's really very similar to other environments. It could be the same to the Raspberry Pi. It could be the same to Android environments, or some modifications, of course, because it's adapted, as the name implies, to a proper environment. It's the same for or more or less for ST. I already mentioned that, and for the MPUs, etc. So we try really to follow this architecture very well for different kind of platforms, for different kind of architectures at the end. So we talk about the platform package, but just now opening the platform package, then you see different folders. One folder is RTE, and that's a so-called runtime environment. Perhaps we start with that first. And in fact, and this is now depending on your chosen license model. Now I'm using the free edition, hence you will find only pre-compiled libraries for various tool chains inside that folder. So that means for the GCC-based environments, we have here the lib EWRTE, so a library Embedded Wizard runtime environment for Cortex M7 based environments for the GCC toolchain as a static library. The same one applies for IIR, the same one applies for Kyle. So these are the simple libraries. However, there's a so-called EWXT RTE, and those XT files are especially those files where customers or you can now make your modifications in order to fit better for your environment. So I'm just showing you these routines. So it's a very stubbed base environment. So it's just one C file, and that C file is now already pre-installed. And usually, as these environments are tested for a dedicated environment, in that case the NXP environment, the RT1050, please do not make any modifications there, because it's tested and it's there. But we have customers, and this is then something that we have negotiated with the customer, that there is the possibility to adapt. Just think about, you have a dedicated operating system and you want to ensure that all memory allocation is routed through your operating system codes, rather than using our memory manager, for example. And this is something which can be adapted accordingly inside this environment. Just have a quick view about different routines. So for example, here's the Embedded Wizard allocate function, which allocates, as the name implies, already some memory for a given size or for a desired size, and in fact it's now set up to use Embedded Wizard's own memory manager. The same one applies for the free. And for example, if you are inside a Linux environment and when you think that the classical malloc implementation is much better, much faster, no worries, you can use that. Just adapt those two functions accordingly. So just use malloc here and free here, and this is fine. And so this one is now depending on your system. Perhaps some very interesting function is the EW panic function. As you see, if there is something not working as expected, for example, good question, what is expected? Usually when you have created an object and you do not have any memory left, just a very worst case scenario, and then you want to address that, then it's not working because the object is null, of course, and in that way, for example, panic is used. Or if you have done some if a font which is required is not there because you have not flashed it, for example, or you want to use a bitmap resource, and the flash inside your system does not include the proper bitmap, then panic occurs, and the question, what should now happen? And as you see, it's a fatal system failure is detected, and the default implementation is to stay here inside a endless loop. Usually when we have customers in the working in the medical area, then this would be a good place to say, okay, now something happened which would not work as expected, and the certification routines say, okay, the system does not run inside this kind of endless loop. Then this is something where the watchdog should be triggered, and the system should be rebooted, should be reset depending on your design requirements, and have that. Console output, as the name implies, this is something which puts something on the serial console. Some requirements, and when you think about which requirements are essential for Embedded Wizard, in fact, we have 4 requirements. So we need to have a 32-bit system, we need to have access to the system ticks, we need to have access to a block of memory, which is then given, for example, the Embedded Wizard's memory manager, some as a working space, and finally, we need to transfer the pixels somehow to the frame buffer. And usually during development time, it could be that something is not working as expected, and the system does not behave as expected, and you might wonder, why is that? And then something which is very essential, that you hook in your console and see if there are any logs printed out. And in that way, it's very essential that you have this function set up in a proper way. So that means the EW console output is working as expected in order to get the proper results on the serial console. Because when you're now talking with my colleagues from the support team and you have a question, then usually they respond, what does the console say? And when you say, I don't have a console attached, this is something that I really encourage you to do during your development time, and to hook in some console output in order to really see any error messages and warnings, etc., that comes from Embedded Wizard. And also when panic is called, then you see EW print panic system halted, then you would already see inside the console that your system is now running inside an endless loop. So please do not throw that away. So please ensure that at least for development time and testing time that this function is working, and so that you get the output of the system, which saves a lot of time when we are helping you, when we are supporting you. So I think this is now something not so essential. Something which is essential is the EW getTicks. This functionality is essential to implement, due to the fact that based on that time, animations, effects, transition, and these kind of time critical stuff is implemented. Also touch recognition, gesture recognition from touch input. If we do not have a proper time base, then we cannot do the proper calculations of the previously mentioned elements, and things get very spooky, or could get very spooky, if the time base is not correct. So this is the place where you would add the proper tick mechanism. And then it's just about adaptations to C standard library function like memset, memmove, memcopy, for example. Classical string compare, string concatenation, etc., etc. So these are just now the basic stuff. Math functionality, which is also there and needs to be implemented, sinus function, cosinus function, etc. But this is now very easy to understand, and as you see, everything is already implemented, and that's it. So in fact, the added requirements now for the runtime environment are structured in roughly about 780 lines of source code with a lot of documentation. So, and the total number of functions can be seen there, and usually allocation and freeze required, console output is required, panic. These are really the key function, and getTicks, the key functions where you should take a look at that closer if you will do any modifications on that. So this is for the runtime environment. Now going one line back inside the platform package, then you see different kind of other environments, and as you see, these are all the color formats that are supported now inside this build environment. So we have index 8, the palette based color format. So one entry inside a color lookup table refers to an RGBA 888 pixel value, and that with 256 entries, so an index 8 based palette-based color format. Luma 44, what we already had before, which is the grayscale format, RGB 565, 888, etc. So just jumping now into RGB 565. Something that you see now in the same way that we already had before inside the runtime environment, we have now different libraries, and we have tons of header files and also one C file, which is the ewx.gfx.c file. So first, let's talk about the libraries. I'm not sure if I've mentioned that before. Customers of the professional edition do not get those precompiled libraries. They get the entire source code of the graphics engine, which is that, as well as the runtime environment. So please then do not include the precompiled libraries into your project. Please include the proper sources in order to have everything as a source code. Of course, you could use your own libraries, etc., or use the pre-installed one, etc. But for the professional customers, they get the source code of those libraries. So what libraries do we have? The same way as before, it's a library, Embedded Wizard graphics engine for Cortex M7, for GCC, IRR, and Keil. However, there are now a lot of other libraries lurking around, R90, R180, R270, and these libraries, also now for all different toolchains, so GCC, IRR, and Keil, all those libraries are now configured and compiled to match a dedicated screen orientation. Going back now to the Embedded Wizard project, when you have profile now for RGB 565, but let's pick now the STM RGB565, for example, then there's another option inside the profile which says what is my screen orientation. And as you see, there's now the normal, rotated 180, rotated 270, rotated 90. And when generating the sources for that selected profile, and if that profile has now another screen orientation rather than normal, then also the bitmaps, for example, and also the text glyphs are generated in such a way that these are already pre-rotated. And why is that essential? Especially for the microcontrollers, it's essential because the graphic accelerations that we are supporting do not support a rotation during runtime by the hardware. So this is a missing feature of the microcontroller functionalities, but this depends, of course, on a per target device part. So this one is not does not apply to all microcontrollers. Depends on the dedicated microcontroller itself. But if the microcontroller does not support a rotation in hardware, then you could select dedicated other screen orientation. Maybe landscape, maybe portrait mode. If you want to, mount your display with another orientation compared to the usual physical orientation of your display. And when selecting that, then the bitmap fonts, bitmaps and fonts are generated accordingly, so that the direct access to the bitmap information is then without any CPU usage. So the access is done in such a way that there's no need to rotate every bitmap information or every bitmap itself accordingly to the selected screen orientation. However, our focus is to have a really lean framework and a very fast framework, and that implies that also the drawing routines, where the graphics engine is suited, or what the graphics engine does, that all these graphic routines are also configured in such a way that they expect that the given bitmap resources are rotated accordingly. And with that, the overall footprint of the unnecessary drawing functionalities are then eliminated in order to have a really condensed and a really lean framework at the end. But that implies that we need to compile for different screen orientations different libraries depending on the selected rotation. And now this is essential when you have now selected inside your profile a different screen orientation, like normal rather than normal, so rotated 90, for example, so rotate 90 degrees clockwise, then you would also need to use the corresponding library. And Embedded Wizard would then generate a dedicated error on the console if you would have selected another library rather than the R90 library in our case for different toolchains. Now, having a look also at the EWXGFX file, opening that, which now opens dedicated graphic acceleration implementation. I do not want to spend a lot of the time because this one, as you already see, is something which now depends on the NXP pixel pipeline in that way, and there are quite so this is not 780 files. In fact, we have here an implementation of 1300 etc. files. So I just want to tell you that this is now the place where dedicated functionalities are used in order to, for this environment to use the hardware acceleration. Something which you already see is the EWBSP display, EWBSP graphics. Those header files are related to our so-called build environment, the target-specific files. So the platform adaptation, the graphics engine for the dedicated platform package now relies on the EWBSP display.h and EWBSP graphics.h functionalities, because they usually need to know how big is the frame buffer, for example, or which graphic functionality is available, so that the platform package itself, okay, what underlying system am I using, how big is it, what color format am I using, am I in the right color format, so double checking which is the screen size, do I have a double buffer, do I have a single buffer, do I have a scratch pad buffer, so just a very small transfer buffer to an external display controller, for example. And this is something why this relation is there. So remember the architecture that I shown before, going back now to the PowerPoint presentation. We have here the platform package, graphics environment, graphics engine, and this one now relies also on the target specific adaptation layer. And this is something that you see while including now this EWBSP display.h and EWBSP graphics.h. So this EWXGFX is now, as the same as the description is, this module implements the interface between the graphics engine and the target specific graphics subsystem, etc. And this is now the place. So same before, please do not make any modifications inside that rather than individually discussed. But if you have any problems and if you want to see why, for example, how this interrupt mechanism is done and implemented, this is the proper place to look at it. And this one is now done for all different kind of color formats. What we have now is RGB 565, and this one now depends for all other, or is the same for all other color formats at the end. Just one remark regarding our licensing philosophy. In fact, we are licensing these two components that we had before. So in fact, the Embedded Wizard Studio and the platform package. In order to get something at your side that you have a starting base, this is something that we deploy with this build environment. And that build environment already now comes with a proper platform package. So if you are now licensing a proper professional or small business edition of Embedded Wizard, then you get this build environment, which is for the free edition, and with dedicated add-ons for the platform package. So for example, libraries in the small business edition, which then comes without a watermark, which is appearing from time to time on the display, or in the full source code when it comes to the professional edition. So the platform package is now a licensed component inside this build environment. However, only with the platform package and the generated sources of your GUI project, an entire application will not be up and running. So we already had this EWX files, EWXRTE.c, EWXGFX.c, and as we already saw here in the EWXGFX.c file, we are now relying on dedicated so-called EWBSP modules. Now opening this so-called target specific folder. The target specific folder is, as the name implies, a specific folder for your dedicated target, and these build environments, as you see here now with IDMX RT1050 EVK, is now tailored and suited for that evaluation kit of the IDMX RT1050, for example. And this one now depends for different other platform package, for different targets and for different environments as well. In fact, inside this target specific folder, we have different kind of modules. We have, for example, clock, console, display, event, graphics, in and out, system, and touch.c. The most important one for Embedded Wizard is of course the graphics, as this one is related to the underlying graphical subsystem, as well as the EWBSP display.c, which comes for the proper frame buffer initialization, and EWBSP touch.c. And as you already see, all those different modules are structured in order to capsulate per se individual peripherals, which are unique and which are coupled and structured depending on their usage. So there's no mixture between display and graphics, it's separated. Or for example, the touch is not bound into display, because usually the touch requires dedicated usage to drivers, for example, as well as display, etc. does. EWBSP system.c, this one belongs to system calls. So for example, let's open that one inside my editor here, and you see there are dedicated functionalities which require to initialize the dedicated BSP now from NXP in that way, as we are here on the 1050 evaluation board. If you have now your own hardware, and if you have your own custom environment, these modules are essential to be adapted according to your design. So for example, open the eBSP touch.c file. Then you see, okay, this one is already implemented for the multi-touch environment. So we have here the Focaltech 5406 driver used, and this one there's a define available which says, okay, this one has, I think, 4 fingers or 10 fingers. I don't know. I need to check that. Anyway, it's already say, okay, where's now my touch driver addressable? And this now is really platform specific and target specific and tailored according to the needs. However, there are a couple of functions which are essential to be implemented. EWBSP touch init, which initialize now that way the I2C configuration. Then we have a done functionality if this is required, and that way it is not. And finally, the so-called eBSP touch get events, which is called regularly by the Embedded Wizard main loop in order to get the proper touch events, etc. And then this is implemented, and as you see, also depending on the rotation, on the surface rotation that you have chosen inside here inside the profile. Now for the screen orientation, this one is also of course taken into account, because changing the rotation of the GUI to be rendered doesn't have automatically an effect on an impact on how the touch coordinates are received. So you need to transfer also the touch coordinates in accordance, of course. So this one is now the implementation for the dedicated platform. It's well documented and can be used for your further references. So this is the target specific. So please, if you have your custom board, my suggestion would be to use now this build environment, get started with an evaluation board to see that this one everything is up and running, and then do the proper adaptations according to your project, according to your hardware layout. For example, for the touch or for the system where dedicated other initialization functions are there, or going back, for example, for the timers and the clocks, and for the RTC if there's one available, and this is something which is done as is. However, something important to know, as I already said before, we do not license the build environment. So the build environment is just a reference for you. It is a template for you in order to get started in a very short way. So this is a template to be used, and you can of course use that for your own application, and then hook in your middleware, your other third-party stacks, etc. However, it's not a requirement. So you can just see how everything is set up, how everything is structured, and implement the same one inside your main application. So it's not essential that you rely on this build environment on our SDK here. So this one is now for the target specific. However, I already said that there's a so-called Embedded Wizard main loop. Where to find that? Now going to the application, and in fact you see a couple of folders. In fact, the generated code, that folder is, as of now, completely empty, because that usually integrates or includes your generated source code that the Embedded Wizard Studio has generated accordingly to your selected profile member. And this is something that you just put into this folder here. Other things like classical main.c or the Embedded Wizard main.c, this is something which is not generated. I already mentioned that before. So these are templates to be used and fully working. So just now open the main.c, which is a very short one. In fact, the question is if we have now this way a FreeRTOS operating system used or not. Let's assume we do not have one, so that means we have just a very simple main application which now calls dedicated functions to our system in it, which is the target specific EWBSP system, and this is now the implementation. The console to have some output. Then this one opens the Embedded Wizard main application. We will have a look at that later on. Print some statistics out there to have something up and running, and then we go into the Embedded Wizard main loop. Finally, if the application should be shut down, which is more essential when it comes to an MPU architecture, where you have an executable binary that gets started and should be deinitialized in a proper way, then EW done should be called accordingly, and some system defined stuff should also then be called in order to terminate the system in a proper way. When using an FreeRTOS, then we also have a main loop, but in that way we are creating now a dedicated UI thread or UI task when it's called to a RTOS environment with a proper stack size, etc., and then the GUI thread is called. Don't be afraid why we call this GUI thread and not task. In fact, this same is then used in other environments where you have a proper thread management and not only a task management. Good. So this is for a very simple main.c as a starting point. The main initialization of Embedded Wizard is done in EW main.c. So let's open that, for example. And inside the description, there is now the very basic description how the main loop of Embedded Wizard is done. In fact, it looks like in such a way, but we will have a look at that later, how it is implemented in a couple of seconds or minutes. In fact, after an initialization, you go into a process loop, so which is then called regularly, and finally we have a done function, which is responsible to shut down the application and free all used resources properly. So, process. What needs to be processed inside one loop? In fact, you should process any data from your device driver. What is now a device driver and what is the device interface? Sorry, this is something that I will not discuss today. This will probably be discussed next week when we have a session about the device interface and how the integration with underlying environments, underlying third-party stacks, your middleware stack, for example, is used, how to exchange data, and this one is capsulated by the so-called device interface, by the device driver. But however, this needs to be processed in a certain way, and how to do that is described now here inside this EW process functionality, and or if there is some data that needs to be processed accordingly. Then usually you could also have some kind of hard buttons, so that means you need to process any key events that you receive from the outside world. So the user presses a button, and this button should then be ingested into the Embedded Wizard application, and how to deal with that. This one is done here inside these processing key events. The same applies for touch events in the same manner. And then there are the next two ones, number 4 and number 5. These are very essential. In fact, Embedded Wizard is mainly based, as we saw last week, on the signal slot mechanism and on dedicated effects. When you have some animation running, if you have some effect up and running, and all those belong basically on a dedicated timer. So you need to process the timer somehow, otherwise your UI would not move or would not be a dynamic UI, it would only be very static. However, signals are emitted to dedicated slot functionalities. We had post signal, we had idle signal, we had the usual signal method, and those needs also to be processed, those needs to be managed, and this one is now in the 5th step. When you would not do that, then you would not get any key events anymore, no touch events. Something, if a timer has been expired, it would not trigger a dedicated slot method. Everything relates on this signal slot mechanism, and hence you really need to process those signals. Finally, now if all the basic functionalities have been processed, so data has been events, the input stuff has been processed, timers and signals have been processed, finally you need to do some drawing, and this one is done inside this 6th item here, update the screen. So all the drawing routines are done and finally pushed to the resulting frame buffer. Last but not least, the function is if you have Embedded Wizard is this follow this object-oriented approach. So that means you can create objects during runtime, and if they are not used anymore, if you have some memory allocated which can be freed, then you also should ensure that this is done in a regular way. Hence, you should now run this seventh item here, triggering the garbage collection, so that previously allocated memory that can be freed and not used anymore is then freed accordingly and given back to the Embedded Wizard workspace, or when using in an operating system, in a Linux environment, for example, given back to the proper heap manager, which is available there. Yeah, and finally the done function, but I think I already explained that. So let's have a look at the proper. By the way, as said during all previous episodes, please have a look at our knowledge base, and there we have a dedicated section which really describes in detail how this main loop is working, how the main loop is set up, what should be done, and why this should be done. So if this is now too fast, or if you want to have further information and more knowledge about this one, please have a look at this article as found inside the knowledge base. Yeah, so let's scroll down a little bit to get an idea how this is done. In fact, we had now inside, so sorry for switching to the main, we have here the so-called EW init functionality, and EW init then goes into that function. And there you see now the clocks are initialized. We have according to the BSP for set time and get time if there's an RTC, for example, but this can then be adapted accordingly to your used system, of course. Yeah, so if you do not have an RTC, then please adapt that according to your requirements. The display needs to be initialized, so that means dedicated frame buffers needs to be allocated and memory mapped depending on the system. Then you need to initialize the touch screen if you have one. If you don't have one, then you can just remove that, of course. Then the so-called memory manager, or the Embedded Wizard's internal memory manager, is initialized. If you do not want to rely on that, then of course you need to adapt that. And then finally, now the graphics engine and the runtime environment of the platform package is initialized. Yeah? So these are the basic steps. This is there. Now Embedded Wizard is up and running. So that means memory manager is there, frame buffers are there, graphics engine runtime environment is there. Now you need to create the object, the application of your GUI application. How to do that? As you see, now we have a new object created by the function EW new object indirect by this dedicated EW application class. So what is this application class? In fact, it's also very easy. Just going back to the studio, you see the profile, and then you see that inside the profile a dedicated application class is set up, which goes to my application. So unit application, class application, and this one is defined per profile. And now in this main loop, then through that constant here, EW application class, Embedded Wizard knows which object should now be initiated and assigned to a proper handle. And just think about, we have a garbage collector, and usually the garbage collector would say, okay, if there is no reference, then it would remove that. So if we would not lock that object later on, by the next call to the garbage collector, our previously instantiated root object would be freed again and done, and then we have no application anymore. So if you create a new object, please take care that you also lock that object now from the C layer, because Embedded Wizard doesn't know where this reference is, or inside it has no further references to that application, and hence it would be removed later on, and the system would now crash in the next coming calls if you would have called the garbage collector in the meantime. So core root initialize, and this is now also something very interesting, because now you see how this initialize function of the core root application comes into play. So coming to the studio, going into the unit core. Just think about the convention that we have. We have here the unit. We have now the class core root. So going back to core, going to the class root, and then you see that there's now the initialize function. And this initialize function is now already implemented inside the Embedded Wizard environment. And that Embedded Wizard now requires a dedicated size argument, which is the entire frame of the element. And this now belongs to the Mosaic framework. I will not dive into that right now, but however, if you are now creating a new object, you should also initialize that. So that means you would now call the proper constructor with a given screen size, so that Embedded Wizard itself, or the root object, in that way the main root application knows how big it is in its size. So very essential. Okay, so we have initialization. We have now our new root application, so the main entry into the GUI application. And finally, we need to create the viewport, and the viewport makes now the connection with my frame buffer at the end, and with my graphics engine. And therefore you create a viewport so that you know, or that Embedded Wizard know where now to put the results into the final frame buffer after we have processed one loop. Finally, we need to initialize now the device driver, but as said, this one belongs now to the next session, probably next week. So we have done functionality, but I think this is now very easy to understand. The same way back, but now with a proper deinitialization function. So we close the viewport, we unlock the object of the root application. We are now reclaim memory. That's the call to the garbage collector. We deinitialize the graphics engine. We get rid of our heap manager, so that means he is deinitialized, and then touch is deinitialized, as well as the display itself, in order to release everything which is not used anymore. So now the essential part comes into place: processing loop. Processing means, as you saw before, we need to process our data from the device interface. This is something that we're gonna be explaining next time, probably, but I think so. So I will not dive now into that. However, next one would be now to receive the key events. If there is any key event, then we are just creating we are just telling the root application, so the root object here, that a dedicated press and release event has been happened by pressing the key, and this can be put into the system. If you have some more sophisticated environment, so if you want to really identify if it's a long press, for example, then you would need to adapt that in a proper way. So going now to the touch inputs, in the same manner as it is done for the key events. So we're just requesting now the target specific adaptation layer to get a new touch event. If there is a touch event, we are processing the dedicated lists of touch events, and putting that now with dedicated other function, and that way drive multi-touch hitting, because it is a multi-touch display in that evaluation board that we are now using, with the proper events. So which finger, for example, and which position, and in case if it is touch down, or if it's a move or a touch up, with the proper states of that touch cycle. Then we have the processing of timers, so that is important to call. We have the management of the lurking around the signals to be routed forward to the proper slot methods. This one is done there, and now the magic one happens in case we have devices. So that means if you have some data from the outside world happening, then this variable would be true. If you have any timers to being processed, if you have any signals, or if you have any events, so like touch events or key events, then if any of these four conditions are met, then there will be some graphical output, nothing more. So, and if it is not there, then no graphical output is done. Embedded Wizard is then not processing any graphical environment. So what are we doing when we are now, if you have any given data from the outside world, if you have any timers looking around to be processed or signals or events, then we're just asking now the core root application, do you need any update? It could be that this will not have an effect on the graphics at all. Just think about the timer needs to be processed, okay, but the timer has not been expired and it does not come to any visible effect at the end. Then there will not be done any graphical rendering at the end. So we're just asking if any update is needed, and if that is the case, then we are simply transferring now the pixels from the internal buffer, if any, from internal system to the frame buffer at the end. Yeah, just for debugging purposes, check memory structure, etc. Call the garbage collector. You already saw that. If you want to have more sophisticated information, how the overall memory usage is, so which objects are now really running inside my target, then you could print out some profiler statistics here, which gives you very profound information how the system is structured. And yeah, dump heap would also give you more information about the memory manager itself. So in case there is no devices, no timers, no signals, no events, we would just wait for the next round. So that means if any a double buffered environment is there, so for the next vsync, for example, or if you have an RTOS environment, we would then wait for the next interrupt, for the next semaphore to be released, etc., depending on the implementation. Finally, we have then the done, but this is now coming later on. Just want to go into this update functionality, just to give you a very brief information. So this is just too much tech talk right now, but the main thing is which kind of so this is a routine where the pixels are transferred now to the frame buffer, and this one depends now what kind of setup do we have. Do we have a classical frame buffer approach? Do we have the scratch buffer approach where we're utilizing the so-called GRAM of that external display controller? And this one is depending here. So in fact, what we're doing, this one belongs into the classical frame buffer approach. We're just then checking, okay, are there any dirty areas? No, so we are only drawing dirty areas, getting the proper bitmap, in fact, so this would be the update rec, getting the bitmap, getting the update rec, and finally in this EW end update, this would then be the place where the pixels are really now transferred to the display at the end. The other one, so not normal one, this would be the case for the so-called scratch fill buffer, and then we're just processing the frames, the dirty area to be updated chunk wise, and this one is just done here where we're just getting different kind of regions, and every region is then updated in a proper way, according to the dirty area, of course. Yeah, so these are the main functions. So the process function, and as said, it's a template, but please ensure that the process signals and timers, etc., that these are done. Stick on those, please. Otherwise we would get mad from a support context. Do your modification as required. If there are any questions, please ask us. This is just mapping for the key codes, the EW get key command function, some system information is printed. Of course, you can adapt that for your final product. No worries in that, but that helps us to understand how you have configured your system, for example. Are you using dedicated features or not? Do you have disabled something, and gives you further information, which is very helpful when it comes to further debugging, for further analysis and investigation in case something has not worked and has not that does not work as expected. So this would be the EW main function. And finally, the last element that I'd like to mention here from the overall structure is this EW config.h file that I'm just now opening inside my editor. This EW config.h file is one place at the end if you want to really quick change dedicated elements inside your build environment. So just having a look on that, for example, now in this for this 1050 EVK environment board, we have set up proper addresses, for example, where the SD-ROM is, how big the SD-ROM is, should we do any CPU load measuring, that could also be helpful to identify any bottlenecks, what are the times for the RTCs, for example. Then something which is more essential is to the configuration of the frame buffer stuff, and I really can encourage you to have a look at the documentation, what these macros mean, and how this everything is structured. And there you find, for example, or just the current configuration, we say we are in a double buffering mode. One frame buffer comes with 480 by 272 pixels in width. It goes to the SDRAM base address, so in that way to the SDRAM, and because it's a double buffering environment, we're just allocating a new, not allocating, we're assigning a new or a second buffer as a double buffer to the SD-RAM, and that's it. And this is something that you can adapt according to your needs, according to your requirements. For debugging purposes, it could also be just to disable this the overall usage of the pixel pipeline, in that way to nail down, okay, if there's something working on or not as expected. Memory pool, just the addresses where the memory, the workspace should be. So this is now configured in such a way that, of course, the frame buffers and double frame buffers are taken into account, and given the rest memory pool now to the system. You could also define an extra pool address in that way. So if you have multiple sections inside your SRAM, for example, you could define there different other regions which can be used now inside your system. Finally, it can be configured for further purposes. So for example, if you really want to nail down which graphical operation, for example, is now used, and is there any bottleneck, then you can instrumentize your code. So for example, EW print GFX tasks would really nail down which call is now done when you have a build up of a screen. So that means which rectangle is now copied, which bitmap is blended, which text is drawn, which line is drawn, etc. And this one is something which can be configured inside this EW configuration, for example. Another thing, when it comes more to optimization and adaptation to the design, is to define the caches and the cache sizes for various caches. So for example, for the string cache, surface cache, as well as for the glyph cache. And finally, we have the max issue task. And now the question is, where do you now find these proper values? Because I mentioned this is an optimization. What should be used? Very simple. Go to the application or to your GUI, run the prototyper, go to the window called memory RAM usage, and then you see that for that application you would have a minimum glyph cache surface with 64 pixels, or the issue buffer would be 6 tasks in that way, and these would be the proper figures that can be used here, for example, for the glyph cache and for the issue task. Just to give you a rough idea about how to define dedicated values now for that proper caches in that way. So this is for the caches. Then another section which I just want to give briefly information about is how bitmaps are treated inside the system. For example, if you have bitmap frames that should be used for playing video, for example, so you would have a bunch of different frames and these should be animated, and if these are compressed, then the usual behavior would be that those multi-frame bitmaps would be decompressed entirely, but when playing back a video with a lot of frames, this would simply overload your your RAM usage. And for example, you could then define, okay, just do a lazy loading. So that means only then if a dedicated bitmap frame is required, then this should be taken into account and yeah, made visible for this bitmap view, for example. Just have a look at that, what this all implies and what these are all about. If you have any questions on that, please feel free to ask. If you're not sure about the meaning, then we are there to help you. So this is ewconfig.c, adapted according to your project, adapted according to your hardware, and to your application at the end. Yeah, and have a look at that. It's well documented and already preset for various evaluation boards. So this is for the source. Now going to the project itself, just make it very brief. What we have is pre-configured projects for various toolchains. Now for the NXP environment, we have, of course, the MCU Expresso, so the own tool of NXP for the IDE. However, if you want to use IIR, then you can use EWARM. If you want to use Kyle MDK with Microvision, then you can use MDK ARM, or a very simple one, GCC based, which is only a makefile with the proper rules and utilities set up and dedicated loaders, etc., that can be used now with a command line build environment. If you want to use that command line build environment, then going back now to the root of the build environment, then you see a batch file which says start GCC build environment, and this is something say okay, yep, you want to start it, then this is something where everything is now set up. So that means GCC environment is there, you have yeah, the linkers, the whole toolchain from GCC, the makefile paths are set up, etc. And then you would have a very easy setup in order to really compile very easily a new created board. It's just a starting guide, a help for you to get started immediately. You do not need to use it for your application. It's just to have something in place which helps you very easily to get started. Yeah, so inside these so going back, application project, for example, MDK ARM, for example, they're the proper project files. There's also a readme.txt, which is essential to read, and something that sometimes customers ask ourselves, why are there these so-called EW post-process commands? This one applies now for Kyle MDK as well as for IIR, the IIR environment. There's also the EW post-process command. These one are used in order to manipulate and adapt the project, so the Kyle project or the EIR project, according to your current GUI project that you have defined with Embedded Wizard. So why is this essential? As you probably, just closing that, as you probably might remember, every unit of Embedded Wizard is generated as a proper C file. So if you would add now a new unit to your project, then this new unit will also be generated as a C file. However, Kyle as well as AIR do not detect this new generated C file, and you would need to add and include that manually. And if you would now define this EW post-process command, like here by selecting this profile here and defining post-process and referring now to the proper command that we had before, so pointing to this EW post-process command for EIR if you're using EIR, or if you're using Kyle Microvision to this MDK ARM EW post-process command, then you have some hooked in tools which would now check if there's a new C file out there and adapt the EIR project automatically, or if you're changing, for example, the screen orientation. So this is for Win32, for example, STM32, so no there, sorry, inside this 565 environment. If you have here this screen orientation, or if you're using now another color format rather than 565, then remember you need to put the proper defines in there and the proper libraries. Then this is something that this EW post-process command does for you automatically. if you do not change, if you do not add new units, if you do not change the color format, if you do not change the screen orientation, then you do not need to use those post-process commands there, as it is then a static project. Of course, if you're then adding some new unit, for example, some new C file, then you would need to add that C file manually to your dedicated project for EAR and Kyle. So this is why these EW post-process commands are there. Yeah, going back now to the application itself, we have generic code, we had project, we had the source. There's also a README, really worth to have a look at it, and that's how the glue layer is, the main application, the projects, in order to create in that way now a firmware. When going to Raspberry Pi, for example, it would be very similar. Not that a firmware is then generated, then a Linux executable binary file is generated at the end. Yeah, so we had application, we had platform package, we had target specific. There are also some third-party stuff required. For example, we are deploying an entire GCC toolchain within our build environment, the make system. Now for NXP, we have MCU Expresso IDE and the SDK, which is deployed, but this is not does not belong to us. This comes just in order to make everything up and running, and to have a very easy environment to get started out of the box. Yeah. So something that I have not mentioned right now is examples as well as the so-called master demo. So perhaps let's pick the master demo first. The master demo, there's a ready-to-use ELF file that can easily be flashed on your system. So if you have that iDynamics RT1050 evaluation kit and you want to see Embedded Wizard just up and running without using the Embedded Wizard Studio, without following the workflow, so generating sources and compiling and flashing, etc., blah blah, then just click on that flash master demo, and then that ELF file will be flashed to your system. Of course, this one depends on your system, so please ensure that you have used and hooked in the proper evaluation board. Do not mix them up, as this could brick your device at the end. Please take care about that. But if you want to have a very fast impression and a very easy impression how Embedded Wizard looks like on your target, and then simply flash that master demo. We call that master demo because it comes with different sub demonstration and sub examples combined into one application, and this is just the master demo. That master demo now comes also with various examples, and this would be now the last environment or the last item for this build environment, and this one are different kind of examples. It very starts with the hello world, very simple one. It also comes with graphic accelerator, which shows a graphical performance on that system. Then we have different kind of other applications, some industrial application like this paper cutter there, or some home appliance application like the washing machine. A game is there, Bézier clock, which shows how this application uses vector graphics, for example. If you're not familiar with different color formats, then please have a look at the color formats example, etc. So these are a bunch of examples ready to be used. So double click on that, open the EWP file inside the studio, generate the sources, and going back now to your favorite toolchain like GCC in that way, or EAR or Kyle, compile the application, flash it to the target, and see how the example looks like. However, if this was now too fast, now I need to go to my knowledge base that I have mentioned so often. So let's go there. And then you see that inside this build environments, so let's stick to the NXP 1050 board, for example, this one also explains what everything needs to be done in order to get started. So which are the prerequisites for the environment? You need the studio, you need the platform package, as already mentioned, you need that build environment, which is there, the zip file. If you do not have it yet, go to the website, register by yourselves, download the 3 items, install it as it is described, and get started. So install the studio, install the platform package, connect the EVK to your PC, take care about the switches, etc. And yeah, let's get started. And then you see this one is here is the master demo as explained here. So go to the master demo directory, execute the batch file /master demo, and then this application will be up and running on your board. And everything that I have now explained yeah, is further explained here on this knowledge base, like for example the main loop, how this one is structured and what is required. So implementing the main loop there, different processes that needs to be done, data, key events, touch events, timer signals, updating the screen, and garbage collector. That's it. So this is all explained here in a proper way. Also the examples are briefly explained what these examples are all about. We had the platform package, we had target specific and third-party environments, and also how you can start with the very first UI example by following these these instructions here: compiling, linking, flashing for the GCC environment, creating your own application if you want to start from scratch. This is something that is explained here. We also have here the post-process commands depending on the used tool chains. We have the console output that I already mentioned. Everything is also explained regarding IIR, regarding Kyle MDK, as well as in that way, in that case, MCU Expresso. And it also comes what things have to be done and have to be adapted if you're using your own custom and unique hardware. And this one belongs to the target specific folder. So now just looking at the watch, I'm so sorry I've spoken a lot. Going back now to the presentation, and I could imagine that there are quite a couple of answers right now. So Christine, are there any in the meantime popping up?
Welcome back from my side, and thank you, Manuel. Now we're coming to the questions and answers part. Questions again from you, from the audience, and answers again from Manuel, as we are already used to it. I pick out the first one right away. How do I render a TrueType font file instead of the pre-generated bitmap font on my target?
Yeah, so rendering a TrueType font. In fact, the default behavior of Embedded Wizard is really to render to generate the glyphs, so the pre-rendered bitmap information of a font into the generated source code. However, it could be that if you have Chinese, for example, as an input mechanism used, or you have a Chinese language and you need to use an input from your customers in Chinese, that would require that you would take care about all different characters that are available inside the Chinese language. And as you probably might know, there are tons of characters in that character set, and if you would now pre-generate every glyph for that or for Chinese, this would simply explode your flash probably. For that, we are offering a dedicated other platform package for every platform, which comes with an interface to a TrueType font rendering engine. So Embedded Wizard itself does not integrate a TrueType font rendering engine, but we are supporting an interface to such external TrueType font rendering engine. Then the customer can choose which TrueType font rendering engine should be used. It could be open source stack, so for example FreeType. It could be some proprietary and commercial editions like Monotype Spark, for example. So there are quite of other engines out there and available. And with that environment that we're deploying, so an interface to that, then Embedded Wizard will not generate the pre-rendered glyphs anymore. It will only say, okay, there's now the font xyz.ttf, and inside your integration and adaptation to that interface, your implementation, you need then to take care to provide that font during runtime. And this could then be that this TrueType font is available as a proper TrueType font inside your system, on a file system if you're using an MPU environment, for example, or it could even be that you have static data blob file as a C array inside your code, which is then referred to that TrueType font file, and that needs to be registered during the beginning of the initialization of Embedded Wizard, and then you can use the TrueType font, the proper TrueType font during runtime in order to render a glyph during runtime, depending on the chosen font, depending on the chosen font family, the font size, etc. However, something important to know, of course, using an external TrueType font rendering engine usually also requires more RAM, as a TrueType font rendering engine also needs to have some workspace in order to do the proper rendering of the TrueType font file. So please keep that in mind, and so this should be also be kept in mind when using such external TrueType font rendering engine.
Thank you again. And the next one is, my chosen hardware is not supported within your list. Will Embedded Wizard also work on my target?
Yeah, usually we say Embedded Wizard runs on every device where you can find a display. And I mentioned that already in the beginning of this session, the 4 requirements that Embedded Wizard has to an underlying system. So 32-bit system, memory, ticks, and a frame buffer. That's it. So if your device is not inside the list, please, very simple, contact us, and we can see which environment would be closed. We have also the possibility to customize a build environment for you according to your specification. So for example, on the MPU space, if you have an i.MX 6 with OpenGL, you will not find it in that list, because unfortunately there are so many different configurations out there. There are so many different displays out there. There are so many different evaluation boards out there. It's really hard to put something on the web which gives the same experience that you see on the microcontroller. Unpack, flash it, and it runs inside within 5 seconds. So this is something which is not so easy to do in the MPU. So for that, if you have an MPU, for example, then we would need your toolchain. We would then compile the libraries according to your needs and prepare a build environment depending on your setup. If you're using Wayland Western, for example, or direct frame buffer, DRM, KMS, whatsoever, without OpenGL or other proprietary graphic accelerations to be used, please let us know. Same for the touch, for example, and then we can customize and create a unique build environment according to your specifications, like for example also screen resolution. Just let us know, get in contact with us, and I'm pretty sure that we can support you and provide you with a proper build environment so that you get started very, very easily.
Also on this episode, I will stick to the 3-question rule. I think this is a good number of questions we can answer within the webinar. The rest of your questions will be answered via email individually. So the last one is, how do I place the resources at a certain section within the Flash?
If you have your custom layout for your Flash, honestly speaking, I need now to have a look at it. And as far as I remember, we have added that functionality some time ago inside version 9.0, I could imagine. Just hold on. Yes, it is. So in fact, we define dedicated sections. Every bitmap resource and every font resource comes with a proper definition of which section to be used. And within Embedded Wizard, you can define with macros EW font pixel section name, respectively EW bitmap pixel section name, where this dedicated resource should be located inside your Flash. Just go to the build environment, search for section bitmap, section font, for example, inside your linker script. Then you see inside that linker script where it is defined, and by defining now the proper section name to your custom sections as defined inside the linker script, then you can freely route and position your dedicated bitmap resources and font resources inside your Flash according to your needs, according to your individual requirements and specifications at the end. Yeah, so I think that's for now. Thank you very, very much for attending this webinar. So this was a little bit different compared to the others. So we were not stuck a lot in the studio. So we dived into the platform package and build environments more on the Explorer on the file system level. And yeah, if you have any further questions, please do not hesitate to get back to us and route your questions to us. We're very happy to help you. And once again, thank you very much for your time. Thank you very much for attending, and would be very pleased to see you next week as well. So take care, stay healthy, and yeah, goodbye.
Thanks again, Manuel. So, after this webinar closes, there's again a poll for you where you can vote for the next week's topic. So please type in one of your favorite topics, and also, if you want, please give us some feedback on today's webinar or on the series in total. Or if there's anything else you missed, you want to know, if you have questions, etc., just let us know in the survey which opens up after this webinar closes. Thank you from my side. I wish you a beautiful rest of the day and hear you next week. Bye.